In this video, I'm going to go through another application of geometric series, and that is the bouncing ball problem. The bouncing ball problem is sort of the premise is that that you've got some building or whatever, and you're dropping a ball off of it, and we may know some percent of the distance that the ball is going to rebound each time. Like if we know that the ball will bounce back up 80% of the height that it fell each time, we could sort of calculate how far it fell the first time, and then how far it'll bounce up and back down the second time, and up and back down the third time. And we could sort of keep doing this and look at the total vertical distance that the ball will have traveled before it finally comes to rest on the ground. I really believe that these problems require a diagram, and so be in the habit of drawing the diagram for these things, of writing them down, and sort of seeing what's happening with the problem. Here's my first example, right? A ball is dropped from a height of 100 meters. So similar to what we had in the previous problem, we've sort of got, the ground here, and there's, maybe a building here. We don't even need to draw the building, but the idea is the ball starts at up here and sort of falls down 100 meters. Okay? We then know that each time the ball bounces, it loses 20% of the height from the previous height. Right? So that means that when this ball bounces back up, it's sort of going to come back up, 80 meters. And then it's going to go back down another 80 meters. So in some sense, that bounce there will have represented 2 times 80. Right? On the next one, we can sort of see what's going to happen here. Right? When it hits the ground, it's going to bounce back up. This time, it's only going to bounce back up 80% of the 80 meters that it fell the first time. So there's sort of the sense of like, all right, well, I'm going to have whatever 80 is times 0.8, and that will happen twice. Right? We could even talk about the next bounce, right? On this one, it will be whatever this height was, but only 80% of that. So you almost have the sense of like, well, there was 80, and on the previous one, it only went 80% of that, and on this one, it's actually only going to go 80% of that, and because we're going both up and down, we'll have 2 of that as well. And so what I hope you guys see here is that this is effectively the setup for an infinite geometric series. Just like we saw in the repeating decimal, this is sort of like an irregular initial term. There was this initial 100-meter bounce, but from that point on, you have this initial bounce, you have 80% of that initial bounce, you have 80% of that second bounce. We can sort of see here that there's a very clear first term, and there's a very clear common ratio, right? It seems to me that my first term in this problem, the first term of the geometric portion of the this part, is the 2 times 80. Right? What's the common ratio? What's happening each successive time? Well, each successive time we're bouncing only 80% as high. So my common ratio will be 0.8, which we could write as 4/5. Right? And the idea is we will figure out what this is, and then we'll add on the initial 100-meter fall that we had. So we can use our formula for this. We can say that S will be the first term, which is 160, over 1 minus the common ratio, which is 4/5. Be careful right there. I actually just did this wrong in the video and had to re-record it. Previously, I just put the 4/5 in the denominator. It's 1 minus 4/5. So don't forget that that's how the formula works, right? So S is going to be 160 over 1/5. So I can sort of, I can just multiply the numerator and the denominator both by 5 to get rid of that 1/5 in the denominator. And I'll find that the total distance traveled in the geometric bouncing part of the problem is 800 meters, right? But that's not the total distance. My total distance will be the 100 initial meters that the ball fell, plus the 800 meters worth of geometric series bouncing part. So my total distance here is going to be 900 meters. So here we have another example of the bouncing ball problem. In this case, a ball is thrown downward off a 20-foot tall roof, and it proceeds to bounce 75 feet into the air. The ball is then known to rebound 60% of the height that it falls from. Find the total vertical distance traveled by the ball. So I'd like you guys to pause the video, sort of see if you can set up your initial, set up the diagram for this in terms of what you're going to label and what you're going to put where. Then check back in with me, and once we have that, you guys can go forward with the computation. So the idea here is that you've got the ground. There's this roof that's 20 feet tall. All right, fine. And the ball is thrown downward off this roof, and from there bounces upward 75 feet into the air. Right? After that time, of course, it's going to fall just as far. Right? And from that point, it's going to bounce back up and back down. So we need to think about what's going to happen here. We're going to have that 75-foot height that it fell from. times it rebounds 60% of its height, so that's 0.6, and we're multiplying by 2 because it's going up and back down. Okay, we're going to repeat this process as well, right? It was 75, it rebounded 0.6, and it'll rebound 0.6 of that, and we'll multiply that by 2 as well. Hopefully when we see all these pieces, we can sort of see that there was this initial height of 20 that the ball was thrown downward, and past that point we have this geometric series that's happening. For the geometric series part, our first term is 150, that's this 2 times 75, right? Our common ratio seems to be 0.6, the amount of the rebound that's happening each time, right? So with those things in mind, if you guys haven't already done the computation work, I'd say pause the video and try that on your own. Your sum here should be 150 over 1 minus 0.6. So that's going to be 150 over 0.4, which is 4/10. I'll multiply top and bottom by 10. This will give me S is 1,500 divided by 4, which is 750 divided by 2 is 375. So 375 is what we get sort of for the repeating geometric part of this problem, right? But then we had that initial 20-foot throw that happened, right? So what we have is we have our total distance, which is the 20-foot height plus the 375 feet worth of bounce that happened. So the total distance here, 395. And that's how we do the bouncing ball problem.